So anyway, I call it God, the Big Bang, and the age of everything, because I suppose if you give the age of the universe, that sort of puts a frame around the age of everything. So that's kind of how it works. And of course, I need to just start with traditional interpretation of Genesis, which the Adventist Church has typically fallen into this category among the evangelical churches, et cetera. This long-held tradition that basically Genesis has to be interpreted literally. And of course, Adventists have a little more skin in the game, so to speak, because we feel like it has to be a literal 7 days because of the Sabbath. And then traditionally, that's meant considering the creation story to be a single event, in the recent past. So everything, the universe, the earth, life, everything in a recent time frame. And of course, that's based on some history. Some of you may know about Bishop Ussher, who was a theologian in the middle of the 17th century. He took all of the genealogies within the Old Testament and strung the years together, and he concluded that creation occurred in 4004 BC. And so that's where we get our traditional kind of 6,000 year age. He was kind of, there were some people that kind of laughed at his result, because he also even told what day creation took place on, which is kind of baffling how he even thought he could identify it that closely. But the day that not only 4004 BC, but there was a date, and I don't remember what date it was, but I think that's sufficient for that time span. And then, of course, today, in our modern world, most young Earth creationists still accept Ussher's chronology. And that's in spite of some things we now know. First of all, he used the King James text, which there's a lot of things we know now that the King James text is not quite complete. Some of the genealogies are problematic. And if we have other manuscripts and so on, we discover there are other names that aren't in all the manuscripts and so on. And so using the King James version, it clearly his date couldn't be completely accurate. And if you start using some other sources, as well as interpolating more names, because we're pretty certain based on the Jewish approach that not all the names are in the genealogy. So some have suggested that if you were to redo something like Ussher's chronology, you'd get something more like about 8,000 or more years. And so those who continue to stick to the 6,000, it's a little baffling that they haven't taken into account the changes in our understanding of the Bible itself. But nevertheless, I think when we look at the ages that are traditionally given by geologists, 6, 8, 10,000 years doesn't make much difference. So short chronology is the typical traditional interpretation that the church goes by. Now, of course, modern science considers the Earth to be a lot older than 6,000 years. Many of you know that, and you probably know some of the numbers. Calculations from the size of the universe and the motions of the galaxies that we see out there and so on, some of the evidence I'll be talking about, leads us to a consensus among at least cosmologists that the universe is about 13.8 billion years old, which is a long time. It's hard to even visualize or really understand that type of an age, but that's the current estimate. And then some of you may have noticed last week, and Lauren alerted me to this. I actually hadn't seen it for some reason in the news, but a astrophysicist came out with some new calculations using some other assumptions in addition to the assumptions used for the Big Bang. And he proposed that the universe is actually more like 26.7 billion years old. At this point, his proposal is quite controversial. Some of his assumptions are not agreed upon by most astrophysicists. So I don't anticipate that this is going to be the new age we're all going to live with, but it is notable that a new estimation is a longer age, not a shorter one. And there's really been nobody proposing anything shorter than about 13.8 billion years at this point. In the early days of the Big Bang, it was a little less than 13.8. That was partly due to the fact that we had limited data sets for galaxies and stuff that were out there in the cosmos. And so with better data, it's now settled around 13.8. And then, of course, many of you probably know also that the Earth has been estimated by geologists to be about 4.6 billion years. So that's our general belief among geologists and scientists, 4.6 billion, based on the dating of rocks using radiometric methods, and especially of meteorites, which are very helpful. because we can sort of estimate when they landed on the Earth, when the Earth was solid enough, and so on. So anyway, that's our this is the framework, at least, that modern science tells us is the correct way to go. So what do we do? What have we done traditionally? How do we approach these discrepancies, clear discrepancies? Because if the Bible says it's 6,000 and science says it's 13.8 billion and 4.6 billion, well, the typical approach up to this point for young Earth creationists has been either to completely reject the scientific consensus, just say, oh, science is wrong, the Bible's right, or there's been many attempts to propose speculative, alternative ways of explaining the scientific data, ways of saying, well, radiometric dating doesn't work the way you think it does. Here's the problem here and here and here, and try and shorten those time spans through kind of manipulating the scientific data in various ways. I have heard a number of young Earth creationists of late, in the last number of years, when they realize that the science really can't be assailed very well, to simply say, well, the Earth and the universe simply appears to be old, that God created it with an appearance of age. And I don't know how many of you, when you hear that, feel a little uncomfortable. It seems like that's kind of weird. It's like God's trying to trick us somehow. So that's been the traditional approach. We just simply say the Bible is correct as interpreted, and we have to somehow make the science fit or ignore it. Now, others, when confronted with such conclusive scientific evidence, have chosen to throw Scripture out entirely, and they become atheists or agnostic. And I think that when presented with this sort of dichotomy that you either have to believe science or you have to believe Scripture, that's kind of the obvious way to go, is that second way, that some people will simply say, well, I'm just, I'm going to go with the science and forget it. And I have long, as a teacher in teaching a lot of Adventist students, I've long said, well, wait a minute, there's got to be a better way. We've got to have other ways of doing this. You can't just throw science out, and we don't want to throw Scripture out. So how can we somehow come to a point where we can still accept the Bible, maybe with some modification of how we interpret it, of course, but still accept the Bible as God's word and still accept science? And so that's been my longstanding hope, is that we can somehow come together and do that sort of thing. Of course, that involves uncomfortable discussions like we may have today over some of these issues. But I think we have to recognize that there are some things that science appears to know, and there are some things the Bible appears to teach that, we want to somehow accept both, but where do we draw those lines? So that'll be part of what we're doing. Now, traditionally, there have been attempts at trying to deal with these discrepancies. One of the oldest is one that some of you are probably familiar with, St. Augustine of Hippo, in a book that was actually about Genesis and whether or not it's literal. So this was actually tackled clear back, 3rd century or so. And this is a well-known quote from Augustine. If you haven't heard it before, I'm going to read it through just so you can hear it. But it's kind of, I think, an important point for us as Christians to take. It says, usually even a non-Christian knows something about the earth, the heavens, the other elements of this world, about the motion and orbit of the stars, and even their size and relative positions. And keep in mind, this is a day and age when there were no telescopes and anything. He's just saying, look at the night sky, you can see these things. About the predictable eclipses of the sun and moon, the cycles of the years and the seasons, about the kinds of animals, shrubs, stones, and so forth. And this knowledge he holds to as being certain from reason and experience. Now, it is a disgraceful and dangerous thing for an infidel to hear a Christian, presumably given the meaning of Holy Scripture, talking nonsense on these topics, and we should take all means to prevent such an embarrassing situation in which people show up vast ignorance in a Christian and laugh it to scorn. The shame is not so much that an ignorant individual is derided, but that people outside the household of faith think our sacred writers held such opinions, and to the great loss of those for whose salvation we toil, the writers of our scriptures are criticized and rejected as unlearned men. Now, of course, those of you that know the history of the church knows that the Catholic Church didn't follow Augustine's advice all that well at times. We do have the situation that occurred with Galileo and others who, presented scientific evidence that didn't agree, and the church didn't deal well with that. So, yeah, they had this nice idea here, but it wasn't really adhered to. Now, our church itself has a bit of a tradition here too. If we just take this statement by Ellen White, and this is from the book Education, at face value, I think it gives us some guidance. Now, I realize that even Ellen White in context probably wouldn't take this quote quite the way that I think we should, but I think the church has, at least attempted to recognize that the two, the Bible and nature, should agree. It's just we haven't agreed on how to do that. So here's this quote from Ellen White. Since the book of nature and the book of Revelation bear the impress of the same mastermind, they cannot but speak in harmony. By different methods and in different languages, they witness to the same great truths. Science is ever discovering new wonders, but she brings from her research nothing that rightly understood conflicts with divine revelation. The book of nature and the written word shed light upon each other. They make us acquainted with God by teaching us something of the laws through which he works. And I think that's a noble statement. I think some of the phrases in this have been emphasized in different ways, and sometimes this has been turned around to say, oh, we'll make science fit what our interpretation of Scripture is, rather than let's interpret Scripture and nature kind of in tandem until we can get the two to agree. So I think we've had some conflict over how we apply this, but it's there. And I think this is a noble approach, a noble idea that we attempted at least. Now, I think the Bible itself does provide some interesting statements. I've always enjoyed Job. It's kind of one of those books that stands out from many others. But this long verse here, it's verses 4 to 11, actually, from Job 38. And I'm not going to read it in detail. I'll let each of you read it here. But it's interesting how it talks about really the mystery. Who of you knows? Who knows how God laid the foundations, and so on and so forth. And I think that may be a more an indication, maybe, that even in the book of Job, that if Genesis actually did give us the exact answers on everything, why would Job even make a statement like this? Because it implies that we don't really know how God started things as well as maybe we think we do. So I think the Bible itself is a little bit more in line also with saying, you weren't there, and so we don't really know. And so as we have in modern times, of course, learned to interpret evidence better in the rocks and in the sky, maybe we're starting to get some of those answers, and they don't have to be incompatible with the Bible. So, well, let's go back and see how did people actually view things in the past. What was it like to be an ancient Israelite? How did they see the universe? And I want to emphasize that, the universe, because we have always felt like we lived in the universe, but the universe was a small place once. And here it is from the Jewish or Hebrew mind. And their view, we don't have any evidence they believe the earth was round or a sphere. So it appears that their view was a flat earth. And you can see here that it's that the land mass is kind of floating on a vast body of water. And you get that impression if you look out from, Europe and Asia and Africa, that everything around us is water. And you can see that above, they had their interpretation of what it was like. And notice it's very small. The stars and the moon aren't that far up there. They're just above the clouds. The sun's up there floating around. And then there's this thing called the firmament, which separates the waters above from the waters beneath. And this is what you see described in Genesis when it talks about the creation of the earth, the separation of the waters. Now, of course, today we know there are no waters up there, but this was the view at the time. This was I guess you'd say, the science of Genesis at that time. And then, of course, there was heaven of heavens, which is even above that. So somewhere out above the waters above was the heavens where God lived, and so on. And so you can see this is a very small place. There's not a lot of space in the universe. We're the center of it. We started out feeling like, yes, we're the center of attention in so many ways. And of course, the ancient Hebrews were not the only ones pondering these things. The universe was small, not only according to the Hebrews, but even to other ancient peoples. And of course, Hebrews believed the universe was created by God. Other peoples by gods, plural typically. And of course, one of the things that Genesis does is set the Hebrew view of the universe quite apart from others, that we had a single God that did this work, not multiples. And the ancient Greeks had worked out a fairly complex system. Aristotle gives us the best view of this. And you can see the ancient Greeks actually did recognize that that everything was spherical. The planets were spherical, the moon's spherical, and so on. And it was actually to the point where the ancient Greeks believed that the sphere was a perfect shape. So everything was perfect up in the heavens. Now, the only sphere that wasn't perfect was our Earth, called the sublunary sphere. And we are on an imperfect surface here, the heavens above, the Earth down here. And but everything was spherical. And but the Earth was the center. So notice that the Earth is the center. Now, not all the ancient Greeks agreed with that, but most of them did, that the Earth was the center. And that got worked out in some detail later on. The Ptolemaic system was one that the ancient Greeks and even up into the medieval period, they believed that, here it is again, the Earth is center and everything orbited around us. Now, if you look at the night sky, one of the weird things that happens is that as you watch planets every night, if you go out and look at a planet where it is against the stars, you notice that it moves in one direction and then gradually it slows down and then it reverses direction and moves back the other way. And so the ancient Greeks figure, what in the world does that mean? If these planets are circling us or orbiting us, how is it that they go through this kind of regressive motion? This retrograde planetary motion doesn't make any sense. And so the Ptolemaic system introduced a secondary set of motions. So notice that each planet is orbiting the Earth, but it's also orbiting a false center there. So it's kind of orbiting in a circle. And that mathematically, this all works. It's pretty amazing that they worked this out. And so mathematically, you can actually describe the motions of the planets just this way. And it actually works, but it's extremely complex. And of course, as we know, it doesn't really describe what's actually going on up there. But because it worked mathematically, it was a pretty good model. And that was how the universe was seen at that time. Now, I put in here this slide just to remind us that the medieval world essentially was at that same place that Ptolemy was. So all the way from the Greeks to the medieval world, it's all the same. And I put a background here of a map. This is the map of the world at that time, one of the maps of the world. And so the Ptolemaic system was the standard. That was how people viewed the heavens. Earth is the center. Everything orbits around it. The Bible seems to imply that. The Earth is stationary. It doesn't move. I mean, who's ever felt the ground move other than an earthquake? We're just sitting here in space. So the universe is, and still quite small, of course, because notice that just up there in the sky, those things are not that far away. Then along in the 16th century, in 1532, we have a bit of a change show up. Now, as I said, the ancient Greeks, some of them did say that the sun was the center. That wasn't a popular view. But Copernicus in 1532 proposed that we put the sun at the center and that the Earth and the planets orbit around the sun. Now, because of the beliefs of the church at the time, the official view was the Ptolemaic view, and Copernicus officially accepted the Ptolemaic view. When he published his book, this was a hypothetical model. Okay, it was just saying, okay, here's a way to look at the universe that makes the mathematics a lot easier. And believe me, it's a lot easier. When any physicist, ask any physicist out there, and you can do all the calculations of where a planet's going to be, a lot easier when you actually have them orbiting the sun where they belong. And so this was really to simplify the mathematics. So the church was actually happy with Copernicus's model, as long as it wasn't taken seriously. It was only considered to be hypothetical. And you could use it to do the mathematics. You could compute, the seasons and all kinds of stuff, and it could help reform the calendar. Church calendar reform was important at that time. So it was all cool as long as you didn't take it seriously. So along comes Galileo, 17th century, and he says, oh, no, Copernicus' model is actually real. This is what it's like. That's what it is. And of course, Galileo had evidence for this. And I won't go into all the evidence that Galileo proposed, but the best evidence is the phases of Venus. And you can actually think about that. Venus goes through phases like the moon, and through just a basic telescopic observations, night to night, Galileo could basically prove that Venus was orbiting the sun and that we must be too. And that made us, that made the Copernican model the correct way to view things. Church didn't like that, of course. So they apparently forgot Augustine, and just said, oh, the Bible's correct as we've interpreted it. And so is Galileo, by the way. and we're not going to change. And so it took some years, but eventually this model prevailed. And of course, going forward from that point, we gradually began to expand the size of the universe. So during the, after the Enlightenment, or during, I should say, the Enlightenment and beyond, we gradually began to get a bigger universe. So we now know the sun's the center. There it is. Sun's the center. The Earth and the planets orbit the sun. The stars, they're no longer close anymore. They're really far out there. They're a long ways away. They're extremely far away. And that became apparent for some reasons I'll talk about later. But we recognized that the universe was a quite larger place than we first thought. They didn't even have the imagining of how big it really is, but it was much bigger than they originally thought. By the 19th century, astronomers recognized that we are actually part of a galaxy, which is a collection of stars, many of whom have their own planets probably around them. At that time, nobody had visualized any other planets, of course, outside of our solar system, but they assumed there must be those out there, and that there were numerous other galaxies, because guess what? Better telescopes, we started seeing other galaxies that were much further away. And then by the end of the 19th century, cosmologists concluded that the universe has always been in existence. And this was what was called the steady state model of the universe, which you might note is pretty much in opposition to the Bible, which essentially says God created the universe, which means it had a beginning. But by the early 20th century, cosmologists had this main theory, and it was pretty much a consensus that the universe had always existed, and it's more or less in its present form. Now, that fell apart gradually, of course, because people started looking at more detail on what's happening out there and at motions beyond our solar system. And as some of those things began happening, one of those was George Lemaitre. And notice he's a Catholic. He was a Catholic priest, actually, a Jesuit astronomer. And he proposed that the universe expanded from a single point. And it wasn't given a name at that time. He just simply said, well, based on what he observed in his astronomical studies, that he thought that maybe, the universe did have a beginning. So it was a steady state, it had a start. And of course, that idea that Lemaitre first proposed gradually became, got given the name the Big Bang. And we gradually developed some other evidence for that. Sir Edwin Hubble, who was looking at the motions of galaxies, discovered that every galaxy that he looked at, first of all, when people looked out there, they thought galaxies some should be coming towards us, some should be going away. But when Hubble looked, he noticed that almost all the galaxies are moving away from us. They're not coming towards us, which, interestingly enough, is very consistent with the ideas of Lemaitre. If all the galaxies are moving away from us, that implies that at some point in the past, all of them started from the same location. Now, some of you might be wondering, well, how is it that they could be all moving away from us? Does that mean we're in the middle of the universe? Well, no, not at all. Think of it this way. If we're a raisin in a loaf of bread, and all the other galaxies are other raisins in a loaf of bread, and as the loaf of bread raises, all the raisins move away from each other. So it doesn't matter where you are in the universe, your observation, that's what you're going to see, is that the galaxies are moving away. And so this was very consistent with the Big Bang theory that Lemaitre had first proposed. And the Big Bang theory, though, of course, was in opposition to the steady state theory of the universe. And even people like Einstein hung on for a long time to the steady state theory. But it gradually began to be displaced by the Big Bang theory. And that's the Big Bang theory is interesting because this statement from Psalms, I think, is much more consistent with that than it would be the steady state theory. Because here is the statement: by the word of the Lord, the heavens were made, their starry host by the breath of his mouth. For he spoke, and it came to be. He commanded, and it stood firm. So the Big Bang could literally be God's method of creating the universe, and that was the view of Lemaitre, and certainly of a number of other physicists as the Big Bang theory began to develop. Now, what is the evidence for it? Because I've had people tell me, "Oh, there's no evidence for the Big Bang." Well, it turns out there's pretty overwhelming evidence if you dig into the astronomy, and there are two pieces to it. The very first piece that I've already alluded to is the expansion of the universe, which is based on the redshift, which I'm going to have to now do a little science here in a moment to help you understand that. Some of you, I'm sure, do already. And then there's the cosmic microwave background radiation that came secondarily. So after the expansion evidence, we also discovered this cosmic background radiation that's also in support of the Big Bang. So here's what we have to do. If we want to talk about the expansion of the universe, we have to be able to measure distances. You have to know, how do I know how far away something is? And so I need to give you a little slight lesson here on how do you determine distances. And some of you have maybe heard the word parallax before. Parallax is a common method that can be used for determining the distance to objects in relation to one another. And most of us that have walked around and we look at something closer to us in relation to something distant, we notice that they move in relation to each other. So notice this picture here. Maybe I should bring up my pointer here, my laser pointer. So notice here, as you're walking past this mountain, there's a tree here that's closer to you. As you walk from one side over here to this other side, you notice the tree changes in relation to the mountain. That's called parallax, and it's a very common phenomenon. And for those of you that are good at math, you already know that you can measure some angles between yourself and that tree, and and knowing the distance that you've walked, you can actually work out how far away the tree is, which is kind of cool. And we can do the same thing in outer space. So astronomers have learned how to do this very same process. Outer space, we know the diameter of the Earth's orbit around the sun, and that's the base of this triangle that you can kind of see here. And we can look at the relationship of stars against the background stars that are further away, and we can measure these angles and so on, and doing a little bit of fairly simple mathematics, we can determine how far away that star is. So people like Hubble began to do that process. We could determine the distance to stars. Now, the problem is that stars in our own galaxy are fairly close, so this process of parallax works quite well, and you can get those distances for many, many stars that are nearby. When you look at galaxies, though, that are further away, they're so far away that the distance that we move around the sun isn't great enough to produce an angle we can even measure. So pretty soon we run out of being able to use the parallax approach. But this is the beginning. Parallax gave us the start. And once we had to move beyond parallax, though, we had to get another method. So how else do we figure out distances? Well, the second method, and that is used for all of the more distant galaxies out there, is to use what's called Cepheid variable stars. So that's what these are right here. And I have a little diagram here showing what Cepheid variables do. They're stars that change in luminosity, they change in brightness. And so over time, and you can measure them in a telescope over time, you can see that they start out rather dim. After a while, they get bright, they get dim again, they get bright again, they get dim again. And they do this in a pattern that's very consistent. So you can measure the amount of time it takes for them to go from their dimmest to their brightest. And it turns out that the period of their luminosity, in other words, the amount of time that it takes to go from dim to bright, is a function, a mathematical function. There's a mathematical relationship between that and their absolute brightness, their absolute magnitude. So we can know how bright that star is. Now, if we know how bright it is, then, and knowing what happens with distance, brightness will drop over distance. We can use that then, and this is getting complicated, I realize, so you don't have to know all the details here, but the point is we can actually measure how far away a Cepheid variable star is using those kinds of measurements. We just measure its changes in brightness and dimness and its period. That gives us its maximum brightness that we know it is. And then we measure what it looks like from a telescope, how bright it is, and we can determine distance from that. And so we've confirmed that this works because some of the Cepheid variable stars are in our own galaxy, and we've used parallax to measure their distance. And we can use both methods. They agree with each other. And so using this now for distant galaxies, we've been able to determine the distance to galaxies that are billions of light years away from us. And some of you may remember a light year is the amount of the distance that light travels in 1 year. And now we've measured the distance to galaxies for which the light has been traveling towards us for billions of years. They're, billions of light years away. So with those kinds of measurements, we can now do a second thing. So this is the really complicated science today. So we talk about the redshift, okay? If you look at the light coming from a distant object in space, we can separate that light into a spectrum. And you can see these spectra here, all the different colors of starlight. And within those colors, you also see some dark bands. Do you see where there's lack of color? There's just these little dark bands where there's no light coming through. Those are what are called absorption bands. Those are parts of the spectrum that are being absorbed by material between us and the object. There are gases in space. There's hydrogen and other things out there that absorb some of the wavelengths of light, and so that leaves these absorption bands that are kind of blank spots in the spectrum. Well, if we look at those absorption bands, and let's say we have an object out there that's stationary, it's not going away from us, not coming towards us, we get this spectrum right here. And if we have an object that's coming towards us, let's say we have a star that's coming towards us, and we look at its spectrum, notice the bands here, this dark band that right here, see this white bar there that identifies this dark band? Notice in this spectrum, it's shifted to the left. So that dark band is no longer there, it's now to the left, and that's towards the blue end of the spectrum. So we call that a blue shift. And this happens because as the light is coming towards us, it's sort of like the way sound behaves. When sound comes towards us, its pitch changes. It actually goes to a higher pitch. And so the same kind of thing happens with light waves, and it kind of goes to a higher pitch. And so we have this shift in this absorption band to a different location. So we can say that this light source, this star, is coming towards us. And then if we look at other objects, and in fact, most objects in space, most of the galaxies out there, we notice that they are shifted to the red direction. So notice this absorption band now has gone to the right. It's called a red shift. And almost every galaxy out there shows this red shift. Now, notice absorption bands don't require us to see the colors. And so when astronomers do this work, they don't bother with color. And besides, color is kind of a dicey thing anyway, coming from outer space. So they do the spectra, but they just do them in black and white. So here's some real data. These are data from actual astronomical observations. And these are from galaxies from different distances. Here's one that's 78 million light years away. And if you look over here, they're looking at two of these absorption bands. They would normally be over here to the left, but they've shifted to the right. The right-hand side of the spectrum is the red end. And so notice they're shifted to the red side. There's a red shift. And here's a Ursa Major, a galaxy in Ursa Major, 1 billion light years away. Notice it's shifted further. Those two little bands right there, those absorption bands, shifted to the right. Going on down, clear to the bottom here to the most distant, one of the more distant galaxies, 3.9 billion. And we've gone further than this now, but this is the furthest one on this diagram. And notice that the redshift has gone way over here. Now, what's interesting about that is that this redshift is seen in almost every galaxy out there. So Hubble and others who've done these observations, we've seen these shifts. And not only do they shift, but notice as the further away the galaxy is, the greater the shift. And the amount of redshift tells you the rate at which that galaxy is moving away from us. And so galaxies that are further away are moving away from us much faster than the ones closer to us. Now, if you think about the Big Bang, a Big Bang's kind of like an explosion. Physicists don't like to call it an explosion because it's not really an explosion. It's an expansion of space and time from a single point. And if you think about it that way, the things that are towards the edges of that expansion are going to be moving faster than things towards the middle. And so, yeah, galaxies that are further away are moving away faster because they're at the outer edges of this expansion, which kind of an explosive-like expansion. And so this is very consistent with a model of the Big Bang. And so this was the first evidence that came out, and most people were pretty convinced. A lot of the steady state people still kind of weren't convinced, but it's pretty convincing to realize that all of these things are moving away from us like this, which really does give us a picture of this expanding universe. Everything is getting, the universe is getting larger as all these galaxies are spreading apart further and further. And what Hubble and others did after him was to take the data from these calculations and plot them on a graph where you have the rate at which these galaxies are moving away from us on one axis. So this is how the rate of expansion, or as they call recession, that's the term used in astronomy. And then the distance away from us on the other axis, and you can see that they form a cluster of points along a line. This is the best fit linear regression of all of these data points. Kind of might notice there's a big cluster of these right here. This was the limit of Hubble's work. And then a lot of these after this were Hubble telescope observations and other better telescopes. And the slope of this line is what we call Hubble's constant. And Hubble's constant is a wonderful mathematical number, because it turns out that we can tell the age of the universe by simply doing 1 divided by Hubble's constant. And so that 13.8 billion year age is simply calculating based on this graph, 1 over H0 or HO, and that gives us the age of the universe. And so because this line now is pretty stable, new data points keep on landing, right along the line, we have pretty much had a 13.8 billion year estimate for some time now. Now, remember that 26 whatever estimate that came out last week, that's using other data than this. So it's a different kind of set of assumptions that I won't get into, and are actually not accepted by a lot of astronomers anyway. So there we go. That's how we get the age of the universe based on the Big Bang. Now, remember that this is just one of the 2 pieces of evidence. The second piece was this cosmic microwave background radiation. There were 2 astronomers back in the 50s that were studying, radiation of various sorts, and they were Penzias and Wilson's their names. They got the Nobel Prize for this work, and they were working with a super sensitive horn antenna. This is one of their antennas that they were working with. It doesn't look much like an antenna, but it's very, very sensitive, and they were trying to measure faint radio waves with it. And in order to do that, they had to block all kinds of other things. So they effectively removed, radar from the things they were detecting with it, and radio broadcasts, and heat from the receiver itself, because this thing's so sensitive, it would pick up heat that was being produced by the antenna itself. After kind of getting rid of every possible contaminating, radio wave, they were left with a background noise that was 100 times greater than they expected. It was a total surprise. They're like, what's going on here? All this noise that's coming in. And the background noise was in the microwave range. It's a set of radio waves of a certain wavelength. And they also noted that it was coming from all directions. There was no particular source. It was just coming from everywhere. And so they weren't quite sure what to do with it. But it turns out at the same time that they were doing this, there were another set of researchers, some astrophysicists, Robert Dickey, Jim Peebles, and David Wilkinson at Princeton University, who were preparing to search this very same set of wavelengths, these microwave radiation wavelengths. They were going to search for these in space because they had hypothesized, and this was based on theoretical models, that a certain level of these microwave radiation emanations should be out there in the universe as leftovers or remnants of the Big Bang. And so a mutual friend contacted Penzias and Wilson and said, hey, this work by Dickey sounds something like what you guys have been finding. So got them together, and they eventually published their findings jointly. And it became the basis for the second big piece of evidence for the Big Bang, because the microwave wavelengths that are so abundant out in outer space represent a temperature that's emanating these waves of about 2.7 Kelvin. Now, I don't know how many of you know Kelvin. It's not the Fahrenheit or centigrade scale. Kelvin is based on what's called absolute zero. Zero Kelvin is absolute zero, where all matter is stopped motion completely. And 2.7 Kelvin is just above absolute zero. And based on theoretical models, the temperature of the universe out there should be about 2.7 Kelvin if the Big Bang happened about 13.8 billion years ago. And these observations are consistent with that. And so this is considered then the second big piece of evidence, because it's so consistent with the theoretical position, predictions. And then also we have now discovered, and this has been done through lots of telescope work from Hubble and other, there's actually been a special satellite that was sent up to look at the background radiation. We now know that the CMB is uniformly distributed across the universe, again, as expected from a process like the Big Bang. So these 2 pieces of evidence pretty much are about as conclusive as you're going to get in terms of, yeah, the Big Bang happened. And so if we go back to Genesis, and you may remember that Genesis 1:1 says, in the beginning, God created the heavens, okay, and the earth. Now it goes on from there. And then another verse a little later says that, and God came to the earth and it was without form and void. And so a number of theologians have said, well, there's kind of this gap there at the beginning of Genesis that we could maybe use to accommodate the Big Bang. And in fact, the Big Bang is a good thing anyway, because it does really say, okay, the universe did have a beginning, and this could be the way that God did it. The Big Bang, could have produced a lot of different kinds of universes, depending on how it played out. But we have a universe, the one we live in, that sustains life. And so the idea here is that God fine-tuned the Big Bang. He's the one that was responsible for it. He got it going, and he fine-tuned it such that the universe, as we know it, resulted. And then, of course, he came later, at a later time, and created life in that universe on our earth, possibly elsewhere. People speculate about that as well. But certainly we know life's here on earth. And so God may have done the universe a long time ago and then the earth. And of course, it's also kind of interesting that the Big Bang is considered to be the origination of space and time. And you know how the Bible describes God, that he transcends space and time. So this would be God creating space and time, at that 13.8 billion years ago. So as I often point out to people, there's really no reason why we can't accommodate the Big Bang. It's actually a very nice way of showing that, God did begin the universe. This is how he did it. Now, we do have other problems with time. So I want to finish today in the next few minutes before we open it up for discussion, just to point out, the Big Bang, great, good, but we do have other problems. So the Big Bang, and by the way, the gap in time, sometimes we call this gap creation theory, that God created the universe first and then life on earth later. And then with that in mind, though, could that mean that God maybe made the earth 4.6 billion years ago? Okay, would that be acceptable? That the geological age of the earth is 4.6 billion, that God created it then, but then he came later and created life at a more recent time. Could the earth be 4.6 billion years old and life be just 6,000 years? Now, some of you may be thinking, oh, well, yeah, what about Noah's flood, though? Because if we're going to interpret Genesis in a very literal way, we do have Noah's flood. That's part of the Genesis story. And by the way, Noah's flood is traditionally placed at about 4,360 years ago. And so what about that? Can we accommodate these kinds of things? Is there signs that life is only 6,000 years old? And what about the flood? Well, let me throw a few wrenches in the works here. And I have intentionally avoided using radiometric dating for these numbers, because I want to show that even if you can somehow twist things around to show that radiometric dating doesn't work, there are still many other bits of evidence that point to the Earth as being quite old, and that life on the Earth is probably equally as old. And so here's some of those. The oldest hieroglyphs. Okay, so the oldest hieroglyphs are estimated to be about 5,200 years old. Although, and I'm cheating a little here because they probably did use some radiometric methods to do some of that to confirm those dates, but those dates are really more based on archaeological comparisons. And so that's a pretty good solid date. And notice that's almost 1,000 years before the flood that we have hieroglyphs. And clearly Egyptian civilization existed before the first hieroglyphs as well. So that pushes human existence past the flood easily. Then we have dendrochronology. Some of you who know about the bristlecone pines and some other trees around the world where they have trees that are quite old, as well as preserved material on the ground from older trees that have died, start lining up the rings in the trees. And although the oldest tree itself is only around 5,000 to 6,000 years old, you can start lining up the rings of the living trees with those that have died, and then you can work backwards from those and line them up with other trees that have died. We now have a record using dendrochronology that goes back at least 9,000 to 12,000 years. So this runs back easily before 6,000 that we know trees were in existence. So that provides some problem with the idea that life was only created 6,000 years ago. And then we have the creosote bush, amazing little plant here in California, grows out in the desert. And instead of reproducing primarily by seeds, which it can do, it often clones itself and forms a kind of a ring. And so it starts with a plant in the middle, and then over time it clones itself, and more individuals kind of end up circling that original plant, and it grows outward and outward. And they have now estimated that some of these ring clones of creosote bush are about 11,700 years old. And so the original, creosote bush in the middle cloned itself over those last 11,700 years to produce these large rings. Then we have what are called varve counts. I don't know how many people know what varves are. They're simply the layers in sediment, because you have these annual sedimentation processes where you have large particles, small particles, and different kinds of things being laid down at different seasons. And you can go and get lake sediments and pull these out, and you can count the varves, just count them, 1 year, 2 year, and so on. And we have, just from varve counting, lake sediments that give ages of at least 50,000 years. And keep in mind that there's pollen, as I say here at the last statement, there's pollen and spores in every one of those layers. Even ice cores, and these go back even further. If you go to Greenland, they have now pulled out ice cores, and they can see the yearly deposition of ice or of snow that went into making these layers of ice. They go back 800,000 years. And even in Greenland, which is a long ways away from, where plants might have been growing, they still get pollen in many of those layers. They go back so many years. So we easily, without even going into radiometric dating or anything, it's pretty clear that life has been around for a long time, multiple 6,000-year periods in the past. And so anything dating before the Noachian flood clearly wouldn't have survived the flood. And so that itself implies that the flood maybe wasn't worldwide. So there are some, creationists that are willing to maybe accept that the flood wasn't worldwide, but, given this abundant amount of evidence. And then there's ages many times in excess of 6,000 years. As I've just pointed out, these also imply that life has been around much longer than a literal interpretation of Genesis might suggest. Now, if we accept radiometric dating, of course, the dates get even older. And so if radiometric dating is serious, if we actually accept that it works, then we have dates for the oldest fossils, and these are fossils of cyanobacteria. These are individual bacterial cells that date to even older, to about 3.5 billion years in age. And so that's considerably older than anything that's 6,000. So what do we do to that? What have creationists, how have they responded? Of course, there's a whole list of responses here that have occurred, all the way from the young Earth approach. The current one is simply to say, okay, well, the data aren't accurate, and you can go out there, all of those things that I showed you about the varves, the rings on trees and stuff. You can go out there and you can find young Earth creationist arguments that tear those all apart. None of those are published in peer-reviewed literature. And aren't accepted by the general scientific community, but they've spent a lot of time in tearing apart the ways of determining those ages so they can kind of try and fit them into this young Earth age. So there are many attempts at that, and that's one approach, to simply say the evidence isn't what what scientists say that it is, because they're not recognizing, like, for example, that tree rings, maybe more than one are laid down per year, and if you had many laid down per year, you could get those tree ring. The tree ring evidence would telescope down to maybe only 6,000 years. And then there's some creationists who do accept a somewhat longer ages, recognizing that Usher's chronology doesn't quite work, and that, we probably deserve a few more thousand years than 6. And so they're willing to go 10 or 15,000 years. But of course, if you start putting in radiometric dating and so on, it really doesn't fit that either. And of course, they are going to then question the accuracy of such measurements, including radiometric dating. And if it doesn't work, then maybe the 10 or 15,000 years is okay. And then many of you are acquainted with intelligent design. Intelligent design proponents believe that there's an intelligence. They don't necessarily specify that it's God. Many of them do, though. But they postulate that intelligence then was involved in the production of the diversity of life over time. So it could be spread back over time. They don't have a problem with long geological ages, but God was involved in, or intelligence was involved in the evolution of these organisms. They didn't evolve by natural selection, but they were helped by this intelligent creative process. And then we go to the kind of the most accommodating approach, which some like Francis Collins, some of you may have read his book that he put out where he relates his way of dealing with the evidence, a thing called evolutionary creationism, which simply assumes that God created the appropriate conditions for the first simple common ancestor to evolve. So in other words, the Big Bang, God arranged it just right so that the universe would expand and that the Earth would evolve out of the materials, our solar system would evolve, and that the conditions would be just right for life to evolve out of that, and so on. So God ultimately is the creator, but he did it through natural processes that he set in motion, that he carefully scaled them to work just right. Some that are maybe more called theistic evolutionists would maybe say God actually directly created the first cells, the first common ancestor. So those are kind of two options there. But this happened a long time ago, maybe 3.8 to 4.3 billion years ago. And then God simply allowed evolution to create the diversity we see. And so that's the very most accommodating approach to kind of taking the science, still taking scripture seriously, because it turns out Francis Collins is a very devout evangelical Christian, believes very much in God's salvific work and so on, but has fully accepted the scientific evidence, and it's an area that maybe many Adventists, I'm sure, find not quite so possible. So anyway, that's where I want to end up, and leave it at this point to talk about what do we do with this stuff? How do we approach it? And what do we think about this Big Bang? Does it work? I think it does. Anyway, so I'll throw it out there.